Okay, people, we should make a start. So, few housekeeping things. Assignment 3 due mid next week. Quiz 4 released tonight, along with the usual stuff, solutions to cheat sheet 6, etc. Let me just give a plug to looking at the solutions, even if you were confident of everything in the tutorial. I think one thing that separates people who do really well in this subject is that they look seriously at, excuse me folks, sorry. One thing that separates people who do really well in this subject from other people is that they look really seriously at solutions. Even if they know how to do it, they're interested to see what's another way to do it, is this the way I'd phrase it, all that stuff. Okay, so next week we've got a public holiday on Thursday, so we're going to miss a seminar. As usual, I'll upload one to Echo 360. I'll do it as soon as I can on the Wednesday. Try and watch it before our Friday one. And the usual drill with applied classes, right? If you're missing your class, you'll get the participation automatically, but we encourage you to show up to one of the online makeup classes we'll put on. A list will be up over the weekend. Any questions on that? Okay, good. So, yeah, sorry.
Can people go into like other in-person ones?
No is the answer. A lot of them, a lot of them are nominally full, right? Unfortunately, most of them won't actually be full, but the official answer to that has to be no. If you happen to find another in-person one and you politely ask the TA and they say yes, that's great by me, but official answer is no. Yeah. Okay. So, probability today. So, why as a computer scientist or indeed as a mathematician might you care about probability? So, a few reasons. So, understanding random algorithms, this is obviously, it's going to involve some knowledge of probability. And random algorithms are really important because there's a bunch of things that if you want to do it absolutely for sure, it can be really hard. But if you're content to do it 99.9% of the time, you can do it really, really quickly, and sometimes doing something 99.9% of the time really quickly is better than doing it every time really slowly, right? So random algorithms are important, hence we need to know something about probability. Just as important is that people act kind of randomly, right? And so if you're serious about modeling the way that users of a system behave, that's probably going to involve some probabilistic analysis too. Same with errors and malfunctions. That can be anything from, the 1 in 1 billion chance that a gamma ray comes through and flips a 1 to a 0 in a system somewhere, through to much more common stuff. Obviously, crypto systems, a lot of, the chance that someone just randomly guesses a key that works is important there, right? And all sorts of stuff, right? You could just go on and on and on about the list of how probability comes up. So I won't over-egg things. Okay, so the idea with probability is that we're trying to model random processes mathematically in some ways. I guess I should have added to this list. I mean, and just because we live in an uncertain world, and I do actually think thinking probabilistically is, sort of useful in terms of just living your life sometimes when you're thinking about risks and rewards and things. Okay, so, so I guess there's sort of two related things with probability. Firstly, some things are genuinely random, or at least as random as things can get, right? Things like, genuinely rolling a dice, or, whether a radioactive isotope decays, or that sort of thing. There's this feeling that they're, in some sense, truly random in some sense. But then there's a whole bunch of stuff that isn't really random in that sense, but is really well modeled by a random process. So, for example, we were talking about errors or something like that. The number of times that someone makes a mistake and has to call customer support, that, or the number of people who are calling a customer support line, that isn't really random. I mean, each person is making a decision based on what they did with that software on that day and whatever else. But if you look at it in aggregate, it's very well modeled by a random thing. So, so anyhow, probability works sometimes with things that are really random, and sometimes with things that are just well modeled by random processes. So let's get straight into the formal definition, and then we'll see some examples of how this formal definition actually works. So probability stuff, in mathematical terms, random stuff, takes place in something we call a probability space. So a probability space is a set S that's called a sample space, and the things that are in the set S are called outcomes. So these are basically the things that could happen, right? Set S of things that could happen. And then a probability function, which people use different notation for, we'll use PR for. And PR maps things in S, so these outcomes, these things that could happen, to real numbers between 0 and 1, right? But it can't just be any old function. It needs to have the property that when you add up the PRs of all the things in your sample space, you get 1. And so the idea here is that 0 stands for impossible and 1 stands for definitely. And you are saying, of all these things that could happen, here is the chance between 0 and 1 that each one will happen, and those chances add up to 1, so they make sense somehow, right? So that's the idea. So a probability is a number between 0 and 1 of an outcome where 0 means impossible and 1 means definite. Okay, so how does this actually work? Well, let's think of a spinner, like the spinner in a kid's game, except let's assume this one isn't, sort of really manky cardboard and it's got a big fold in it and keeps stopping in one place. Let's assume this one genuinely works like you would expect it to. So, we could model this spinner with a probability space. The sample space would be the set 1, 2, 3, 4, because we're assuming it always lands on a 1, 2, 3, or 4, never on a line between things. And we would say that the probability of 1 was a half, because this is about half our circle. probability of 2 is a quarter, and the probability of 3 and 4 is about an eighth, right? And notice, of course, that these things add up to 1, like they have to in a probability space. And often we'll just write that as this is a table like this. Here are the outcomes, and here are their probabilities. Does that make sense? Cool. Notice, though, that these things do not have to be equally likely, right? In this case, our basic outcomes had different probabilities from each other, right? So, and this is important because, but of course, you know, sometimes things really are equally likely, right? If we roll a genuinely fair six-sided die, then our outcomes are 1, 2, 3, 4, 5, or 6, and each of them has probability 1/6. And so those are important types of probability spaces. They're called uniform spaces, sometimes called a uniform sample space. And the jargon that people use is that doing this is like selecting a number from 1 to 6 uniformly at random, right? So if you hear uniformly at random, that means all the things, all the possibilities are equally likely, right? So it's not always like that, but when it is, you say uniform sample space and uniformly at random. Okay, so, and in particular, let me just make a note. We'll see this again a bit later, but in like primary school, I think I was told that, you know, the way to calculate a probability was to find the number of outcomes that worked divided by the total number of outcomes, right? And that works in a uniform space, but it doesn't work elsewhere. So we'll come back to that. But that is not always a rule you can use. Okay, so we've had the basic atoms in our sample space. They were called outcomes, right? So they're sort of the basic things that can happen. But often we're interested in sort of combinations of them, right? And those combinations we call events. So an event is a subset of the sample space. So let's think of the die rolling example. Our outcomes there, our basic outcomes are just 1, 2, 3, 4, 5, and 6, right? But then we can take them and we can build up all sorts of different events, right? So we could have the event that you roll at least a 3, right? And that would be represented by the set 3, 4, 5, 6, right? Because that's all the things that are at least 3. Or we could have the event of rolling an odd number, which would be the set 1, 3, 5, right? And we talk about the probability of an event as the sum of the probabilities of all the outcomes here. So one thing that's sort of important to note is the outcomes are the basic things that happen. Only one of them happens in a probability space, right? Each time you just get one outcome. But of course, events being just sets of outcomes, you can have lots of them happen at the same time, right? If I have, you know, if I roll a 5, that is both satisfying the event it's an odd number and satisfying the event that it's at least 3, right? So events can overlap in all sorts of ways, whereas outcomes, only one of them happens each time. So The picture, this was the dodgy clip art picture we used for subset, and it's also sort of the mental picture you should have of an event, right? B might be a whole sample space. A is an event within that sample space. You're choosing some chunk of outcomes and you're saying, this is the event I'm interested in. Okay, so for example, we might have the event 1, 2, 4 with our spinner, right? So the event that we don't spin a 3, basically. Well, then the probability of that event is the probability we spin a 1 plus the probability we spin a 2 plus the probability we spin a 4. And if you remember, that was a half and a quarter and an eighth, which was 7/8, right? Now, and this is what I was saying earlier, in a uniform sample space, remember all outcomes equally likely, we can calculate the probability of an event as just the number of outcomes divided by, number of outcomes in our event divided by the total number of outcomes, because they're all equally likely, right? But notice that doesn't work with the spinner, right? Here there were 3 outcomes we were interested in. There were 4 possible outcomes, but the probability here wasn't 3/4, right? Because the outcomes weren't equally likely. So you can use this formula in a uniform sample space, but you can't use it in general, right? Okay. So, as an example, here's a probability space. Our possible outcomes are 1 to 5. And our probabilities look like this. You can check that they add up to 1, because they should. So let's think of 2 events. E is the event that we get an even number, and P is the event that we get a prime number. So firstly, what is the set that E corresponds to? 2 and 4, right? The set containing 2 and 4. What is the set that P corresponds to? 2, 3, and 5. Absolutely agree. Okay, and then what is the probability of E? Well, we've got to add the probability of 2 to the probability of 4. That's just a fifth plus a fifth, which is 2/5. Probability of P is 2 plus 3 plus 5, so a fifth plus 2/5 plus a tenth, which comes out to 7/10, right? So far so good. Okay. So, events are just sets, and we can do set operations on them, right? But sometimes these set operations are particularly useful for events. So for example, if I'm interested in the event that either event, I shouldn't have said either, if I'm interested in the event that A happens or B happens, or both, then that's just the event A union B, right? One of the outcomes in A or B or both happens. If I'm interested in the event that both events A and B happen, then that's A intersect B, right? One of the outcomes that's in both events happens. And also complements are very useful here. A bar is going to be the event not A, and when we're working in a probability space, the convention is complements are always relative to the whole sample space, right? So this A bar means everything in the sample space minus the stuff in A, right? So you should be able to translate between the English and the set notation here. That's a useful thing to be able to do. Okay, so going back to our example, remember we had numbers 1 to 5 were our outcomes, evens, primes were our events. So what is the event E intersect P or E and P? It's just 2, right? That's the only even prime number, so E intersect P is 2. What's the event P bar or not P? Yes, 1 and 4. And the event E bar or P, not E or P? 1, 2, 3, 5, right? So everything except 4 there. Good, good. Okay, so this is an unfair question because you don't have the necessarily the required theory yet, but well, maybe it's not totally unfair. Definitely one you have to think about though. So worth talking with your neighbour about this. Tell me which of these equalities or inequalities you think works for the probability of A and B. How are we going? Another 30 seconds. Okay. So, most of you are wrong, but you're wrong in a good kind of a way. So, I want you to think about rolling a dice, right? So let A be the event that you roll a 1 or a 2, right? So probability 1/3, right? Now, let B be the event that you roll a 6, but this is all on one roll of the dice, right? So what is the probability that you roll both, probability 1/6 for B? What is the probability that in the same roll you roll both a 1 or a 2 and a 6? 0. Right? It's impossible to roll less than 3 and 6 simultaneously. Right? So that tells you that this probability, none of those top ones are going to work. Right? Because none of them would give me 0 in this case. And then if you think about, you can think about another situation, which is A is still rolling a 1 or a 2, now B is rolling a 1. What's the probability I roll a 1 and a 2 and a 1? Well, that's just the probability I roll a 1, which is 1/6. And those are sort of the two extremes, right? I could be at 0, or I could be at the smaller of my two probabilities. And I could, if I set up my space right, get basically anywhere between those two. But, so that's the answer there, E. The only thing you can really be sure of is it can't be more than the smaller of the two probabilities. But the answer that most of you gave, probability of A times probability of B, is the right answer in a specific circumstance, which is where A and B are what we call independent events. And we will be getting to them in like 3 slides' time. So hold on for that, right? And in fact, the fact that probability of A intersect probability of B is equal to this is actually the definition of events being independent. Okay, so first I want to talk about the probabilities of unions of events. So remember last seminar, inclusion-exclusion told us that the union of A and B, the size of that, is the size of A plus the size of B minus the size of A intersect B for finite sets A and B. So we can repurpose this in probability and say that the probability of A or B is the probability of A plus the probability of B minus the probability that both A and B happen, right? For exactly the same reason that this works. So if you think about rolling a dice, and we have A is rolling a 1 or a 2, B is rolling a 2 or 3 or a 4, we can work out that probability as 2 on 6 is our probability for A, 3 on 6 is our probability for B, our probability that both happen is 1 on 6, and we get total probability being 2/3, right? And so obviously you can't always say that the probability of A or B is just the sum of the probabilities. But sometimes you can, right? If the two events cannot happen together, so if the probability that both happen, that A and B happen, is 0, then of course this equation just simplifies down to probability of A plus probability of B, right? And when two events can't happen together, they are called mutually exclusive, and we can just add those probabilities. So mutually exclusive because each one excludes the other, right? So two disjoint events are mutually exclusive. So this is going to seem terribly simple to you when I say it, but then I guarantee you some of you are going to get mutually exclusive mixed up with independent when they're very different. So this is half of something I'm going to try and tell you not to get mixed up with something else in a minute. So read it like this. So mutually exclusive events cannot occur together. So if we roll a standard die, then the number rolled is at least 5 and the number rolled is 2 are mutually exclusive, right? Cannot occur together. The number rolled is even and the number rolled is 6. Are they mutually exclusive? No, they definitely can occur together. So in general, for any two events, doesn't matter if they're mutually exclusive or not, we can always use this formula. But for mutually exclusive events, this bit is 0, and we can just add the probabilities to find the probability of A or B. Make some sense? Okay. So mutually exclusive, in my head, it's kind of an easy concept, right? It's just they can't happen together. Now, independent is the thing that some people are going to get mixed up with mutually exclusive. Independent is much trickier, I think, at least to think of. So the formal definition of independent events is that the probability of A and B is the probability of A times the probability of B, right? But that's one of those definitions that, in my head at least, it's just sort of a formula and it doesn't give you too much intuition about what's actually happening here. So let me tell you how I think about independent events. I think about independent events by imagining trying to cheat on gambling games, right? So you're in a movie like The Sting or something like that. And independent events are ones that don't, so remember, mutually exclusive events just couldn't happen together. Independent events don't affect the likelihood of the other. So if you know about one, that doesn't give you any information about the other. And that's why I think about them in terms of trying to cheat on gambling or something. Imagine that, you know, I'm playing a gambling game where someone rolls a dice secretly and I have to bet on whether the number rolled is at least a 5, right? And I've set it up so there's a secret camera and I have an accomplice in another room and he's looking through the camera and he says to me, oh, I can't quite see it, but for some reason I can definitely tell you that this number is even, right? So he's told me the number is even, I've got to bet on whether it's 5 or more, and he has been absolutely no bloody use at all to me, right, when you think about it. And the reason is because these events are independent. So let's think about why. So, we can think about this in either direction, right? But let's think first about the direction I was talking about. Before, when I didn't know anything, when I hadn't talked to my accomplice, I was thinking, well, there's a 1/3 chance that this dice rolls 5 or more, right? And now my accomplice has told me that the number is even, so it's now equally likely that it's a 2 or a 4 or a 6, and there's still a 1/3 chance, right, that it's bigger than 5. So that's why it hasn't helped me. It's given me no new information. And you can also think of this backwards, right? If I was betting on whether it was even and my accomplice told me it was greater than or equal to 5, the same would apply. Even has a base probability of a half. If I know it's greater than or equal to 5, then it's out of 5 or 6. It's still a probability of a half that it's even, right? And this was the direction I just talked my way through. And that does actually correspond to the fact that if you think about the probability it's greater than or equal to 5, that's a third. Probability it's even, that's a sixth. And the probability that's greater than or equal to 5 and even is also a sixth, right? That's the formal mathematical definition coming in there, right? But now imagine that I'm betting on whether the number rolled is at least 4 or not, and my accomplice tells me it's even. Suddenly this is really useful to me, right? Because now I know it's either a 2 or a 4 or a 6, and I know there's actually a 2/3 chance that it's 4 or more, when before I would have thought there was a half chance it was 4 or more, and presumably somehow this helps me bet better, right? So that's because these are not independent. One of them gave me information on the other. So even number has base probability a half, but probability 2/3 if we know the number rolled was at least 4, and greater than or equal to 4 has base probability a half, but probability 2/3 if you know the number was even, right? So those are events that tell you something about each other, so they're not independent, and you can check that using the formal definition. So probability greater than or equal to 4 is a half, probability even is a half, that when you multiply them you get a quarter, but probability greater than or equal to 4 and even, that's the probability of a 4 or a 6, and that's 1/3. So these two are not equal, they're not independent. Does that make some sense? So big picture, remember mutually exclusive means cannot happen together. Independent means don't affect each other's likelihood. Mutually exclusive events can't be independent unless one of them was impossible to begin with, right? Which is kind of a stupid situation. So any two non-trivial mutually exclusive events can't be independent. Okay, so try not to get them mixed up. I actually want to go back for just 1 second, because there was one thing I should have said when I came here. Like sometimes events are independent in an obvious way for really obvious reasons, right? Like if I roll a dice and then I roll the dice again, then it's obvious that my first dice roll doesn't affect my second dice roll. At least hopefully it's obvious, right? You know, the dice doesn't have a loaded number of sixes that it's going to supply over time. So those kinds of events are independent for obvious reasons. But this sort of thing is an example of how, like when you look at this, you know, the number rolled on a dice is at least 5 and the number rolled is even. I mean, it's about the same dice roll. You'd sort of think, oh, probably they are not independent, right? Probably they are dependent. But that top one is a case where sort of magically the numbers work out in such a way that one doesn't tell you anything about the other. So sometimes things are independent for obvious reasons, but sometimes they're independent for sort of tricky mathematical reasons, right? Yeah. Okay. So, okay. What have we got left? Okay, we've only got a little bit left, so I will go through this in a second. So, just as an example, imagine generating a binary string of length 3 uniformly at random, right? So that means, remember, that all of them are equally likely. There are 8 binary strings of length 3, so each occurs with probability 8. So the event that the first bit is 1 is independent of the event that the second bit is 1. So let's check that. This is all the ones with the first bit 1. This is all the ones with the second bit 1. Obviously, they both have probability 1/2, 4/8. Now, probability of both of these happening is the probability that I get one of these two strings. So that is 1/4. And 1/4 is 1/2 times 1/2, so that meets my definition of independence, right? But now imagine I've got another event, C, which is the event that the string contains exactly 2 ones. So that's this event here. It's 3/8 probability. Now the probability that the first bit is a 1 and that the string contains exactly 2 ones is the probability that one of these two things happens. So it's 1/4, but when I multiply 1/2 by 3/8, I get 3/16, which is not 1/4, right? So that's using the definition of independence to show those two events are not independent. Does that make sense? And in general, if a question asks you whether two things are independent, you should go with the mathematical definition, right? That's better than trying to give some intuitive explanation about why they are or are not independent, especially because things can be independent for sort of weird, tricky reasons, as we talked about, right? Okay, so we'll finish up with a flux question then, trying to get at the intuitive idea of independence here. Good one to talk about.
When you say the professions, are they still a jockey or still a basketball player, or like they can be retired?
Let's say that they are currently, they're currently those things. So no retirees. They have to be currently earning a living. another 30 seconds. Okay. Have a guess if you haven't answered yet. All right. So, I like your answers by and large. So let's work our way through this. So let's start with E. So I reckon being over 75 affects all of these things, right? So firstly, if you're over 75, you're less likely to be employed, so you're less likely to be a lawyer, and you're certainly much less likely to be currently a professional basketballer or a jockey, despite the wonders of modern medicine that's still probably out of the reach of most 75-year-olds. You're also a little bit more less likely to be tall. Why is that? Sorry? Well, sorry, yeah.
I also think there's two reasons. One, the only one is less likely you'll be hunched over, you'll be less tall. And two, back if you're like older, the average height was much shorter back then.
Yeah, so I think there's the two arguable reasons here. It definitely is the case that people hunch over a bit and things as they age. But more importantly is the fact that each generation, by and large, for the last little while has been significantly taller than the one before it, right? Just better nutrition and that sort of thing. I think that's tailing off a bit, but anyhow. So being over 75 affects all these other things in some significant way, and so it can't be anything to do with E. So now, let's go back to D. If you're over this much tall, then you're more likely to be a professional basketballer and less likely to be a jockey. So it can't be D and A or D and B. And obviously, if you're a professional basketballer, you're less likely to be a jockey and vice versa. And I think that has left us with the only pair that seems reasonable being a lawyer and being over 180 centimetres tall. Even that, I will bet you, is not going to be perfect. There's going to be some sociological research somewhere that says if you're a big tall person, then you're more likely to command a courtroom and, all this sort of thing. But that's probably going to be the closest to independence. Okay, people, have a good weekend. I will catch you next week. Thanks.
I have some question
Yeah.
about the Haas diagram for the
Uh-huh.
order relation.
Yeah.
My nose is a mess right now.
No worries.
Which pages is it in? Actually, I'm gonna draw.
Okay, go for it. Yep. Yeah.
Can I just check? Because for next Friday, they're saying there's a second.
Yeah, no, ignore that. I've asked them to get rid of it, but apparently they haven't. So
Okay,
we'll just put the recording up instead.
Okay.
I don't want to force people to be doing something at 6 to 7 on a Friday. Yep. No worries. Yep.
say 5:30.